Hello, this video will cover some of the topics in chapter 2.1 in the Precalculus with Limits book. The book that I'm referring to, the main authors are Ron Larson and Paul Battaglia. So we're just going to go through some of the topics with sample problems. It's not comprehensive of the entire chapter, so you would do well to kind of go back and look through it yourself, fill in any gaps based on the notes that the chapter gives or examples. So let's get started. This is about quadratic functions and models. What the chapter itself covers are those three learning targets: analyzing the quadratic graphs, writing the functions in standard form, and using the results to sketch the graphs. When it says standard form, this book actually, what they call standard form in this book, most of us call vertex form. And the other learning target is using or finding maximum minimum values of the quadratics in the real life applications. Quadratic graphs show a lot of different things. One thing that it does would be the axis of symmetry. So what is the value that you can fold the parabola on there that it will match up with itself? The axis of symmetry will actually be through the x value of the vertex. So again, my assumption, not again because I haven't said it yet in this video, but my assumption is that you've had a strong course of Algebra 2 before. You're studying Precalculus, so you would have seen quadratic functions before. When I talk about the vertex of a parabola or a quadratic graph, that should make some sense to you. The maximum and minimum is actually the vertex itself. So that is the vertex of a parabola. And if the parabola opens up, then you will have a minimum, and if the parabola opens down, the vertex would be a maximum. The orientation of the parabola is also something you can see by its graph, and that is just whether it opens up. So does the parabola open up or down? In a minute, we're going to look at the standard form of the quadratic functions, and from that point, you'll be able to tell whether just by looking at the equation, you'll be able to tell whether the parabola opens up or down. Here's standard form. Let me just stretch this out so it looks a little bit better. F of x equals ax squared plus bx plus c. You probably saw that last year or whenever you took Algebra 2. And the a value, the b value, the c value, those are all just numbers. So, and we're actually going to refer to those as the a value, the b value, and the c value. The a is always the coefficient in front of the x squared term. The b is always the coefficient of the x, which I would call the linear term, and the c is the constant. It has no x. The vertex form of a parabola is right here in the middle. F of x equals a parentheses x minus h squared plus k. And what that can tell us just by looking at it, the vertex happens at the value h comma k. So once you have an equation that's written in vertex form, and again, the textbook that I'm using in this class, they call it standard form, you can immediately grab the vertex. So that's very handy. And let me grab my text tool so I can stretch this back up so you can see it. For the factored form, this actually isn't a formalized equation per se. I just wanted to show it to you that somewhere in there you might get a factored form, and it allows you to get the roots really, really quick. So if you're given a quadratic or a trinomial, say, you wanted to factor that out, you would have factored form and you can get the roots or the solutions really quickly. In standard form, again, I put that at the top, what it looks like. The a value, if the a value is greater than 0, then the parabola, oops, let me move my cursor out of the way. The parabola will open up. And if the a value is negative or less than 0, then the parabola will open down. And I did put a little note down there. What happens if a equals 0? Well, if you look at the equation and a equals 0, we don't have that x squared anymore, and we just end up with a line or a linear equation. So let me just finish this one. The parabola will open down. The other statement at the bottom is a good thing to kind of make note of. The a value determines how wide the parabola is. If you have y equals ax squared, that a value, the coefficient, determines how wide or narrow the parabola is. The smaller the value of the absolute value of a, the wider it will open. So in other words, if you have like a fraction like 1/4, or say 1/3, or 1/8, that means that the parabola is going to get a lot wider. Okay, let's move on to the next one. We're going to do a couple of examples in a minute on converting from standard form to vertex form, and you're going to have to know how to complete this square. That should have been covered in your Algebra 2 course. Why would we want to do this? So there's a couple things. Standard form, you have to manipulate to use that form to graph. So if you just do a conversion over to vertex form, you can find the vertex really easily. It can help you sketch the graph. It also really points out the shift of the parent function a lot more plainly. And it also, since we have the vertex coordinates, we can find the axis of symmetry really easily because the axis of symmetry goes through that x value of the vertex. And we can generally find the roots very quickly as well. So if we use vertex form to find the solutions or to solve the equation, that's helpful. I'm just going to scoot forward and see if I have that. Nope, that's going to be something that we do in a minute. So what I'm going to do now is a couple of examples on paper, and our task here is to convert to vertex form. So this will just incorporate completing the square, and I'm going to assume that you have seen that before. So the first thing we do, since we are converting over, I'm going to keep the y there. We copy the x squared, and we copy the 8x. I'm going to leave a little bit of space, and I usually put a line just to remind myself that I'm going to add or subtract a number, and then I'm going to bring this minus 20 over as well. The way that so some textbooks call this like the magic number. We need to figure out what to add here so that we can get this into vertex form, and the way that you do that is you take your linear coefficient and you divide it by 2. That will give us 4 in this case, and then you square it. 4 squared will be 16. So notice that we got a positive 16. It was a positive 8 divided by 2, so we're just going to add 16. And then to keep this like a legal equation, we could also add 16 on the other side, but I am going to just subtract 16 here. I'm kind of hesitating because if you look up here, I've seen it written some ways. We have the vertex value for x here, and sometimes they put it on the other side of the equation, and sometimes they don't. So I'm going to do it the way this textbook does it, and that is by keeping this value on the other side of the y. Now what we can do is we can turn this part of the equation. It factors out really nicely. That's why we chose the 16. And what it will factor into is x plus 4 squared. And then if we combine these here, we have minus 36. And that's what y is going to equal. So this is now actually in vertex form. So what we can do is find the vertex, and the vertex is going to be at -4 and then 36. Actually, it would be positive 30. Yeah. So we have a -36, so positive 36. Okay, close parentheses. I think I'm ready to flip this over and hope I have another one written down. Yep, convert to vertex form. And this time they're asking us to also find the solutions, and that's just another step or two beyond what we just did. So again, the same idea. We have y equals, I'm just copying. Now I'm going to leave a little bit of space because I'm going to add a number, and then I'm going to do minus 24. What we're going to do now is find that magic number. So we take -2, divide it by 2, that gives us 1, and we have to square that, and that's what we're going to add. And then we're going to subtract it on this side as well. So if we added the one, we subtracted the one, we've kept it legal. Notice they're on the same side of the equation. So when I go to clean it up, I'm going to factor this. And again, that magic number of 1 allows us to factor it as z minus 1 squared, and that's what we want, minus 25. So right here, I've converted this to vertex form. I could stop if that was all the directions said to do. What I'm going to go ahead and do now instead is I'm going to find the solutions. So the solutions are the same thing as the zeros and the roots, which means y is 0 in those instances. So I'm taking out y and putting in 0, copying all of the rest. To solve for z, usually there's an x, but now they gave us a z this time in this problem. what I'm going to do is bring the 25 over. And then you can see that what I have here is I have the squared term is isolated, so I can square root both sides. And as I look at this problem, I realize, hey, they gave us a problem that's also a perfect square. So the square root of 25 is plus and minus 5. The square root of something squared, it just pops out. They kind of cancel each other out is what happens. So if I'm going to flip this just in case some people watching this are visual. I'm just changing the sides, what's on each side of the equal sign. So now what I'm going to do is I'm going to add the 1 to get the z by itself. So z is equal to 1 plus and minus 5. And so I just evaluate each of those. Z is going to equal 1 plus 5 is 6, and 1 minus 5 is negative 4. And so those are the solutions to this equation. If we were to graph the parabola, we know that at 6 and negative 4, those are the roots of the equation. Remember I said the a value tells us whether it opens up or down. There's no number in front of the z, so our a value is understood to be 1. So we know that this parabola does open up. And if we wanted to find the vertex here is at 1, comma negative 25. So it would be it'd be way down here somewhere. But we do know, like, we could sketch it kind of really quickly. We know that our parabola would hit the vertex and bounce right back up. So we got a lot of things. By converting to vertex form, we could see the vertex itself, the coordinates for it are there. We got the roots really quickly by square rooting both sides. And the original equation also told us that it's a parabola that opens up. All right, I'm going to do one more. If you feel brave and you want to hit pause and try this on your own, I would suggest it. Our directions say to convert to vertex form and then find the roots. So it's the same as the last problem that we did. So again, I'm going to keep the y for now, copying, and I'm going to make some space to add a number. And then I'm bringing that plus 1, and then I'm going to subtract that same number. So that way I'm not keeping the equation unbalanced. To find the magic number, divide negative 4 by 2. It honestly doesn't matter if you keep the negative with it because we're squaring it, and squaring any number is always going to be positive. So negative 4 divided by 2 is technically negative 2, and negative 2 squared is 4. Okay. When I go and take my next step, y equals x minus 2 squared. And then when I combine this part, plus 1 minus 4 gives me minus 3. So that is vertex form right away. I know that the vertex is going to be at 2 and negative 3. So that's a help. And now if I wanted to get the roots, I'm going to take out the y and put in a 0. And then just solve it for x. So we want to isolate our squared term. So we bring the 3 to the other side. Because we need to undo a squared term, we need to square root. And when we square root a number like this, what we have to remember to do is put the plus and minus. Square root of 3 equals x minus 2. We're going to add 2 to both sides. So I'm just going to write it out kind of a little bit more straightly here. What we're going to evaluate is 2 plus and minus the square root of 3. And those are our roots. Okay. So whatever 2 plus the square root of 3 is, and whatever 2 minus the square root of 3. Those are our roots. We have the vertex. And again, if I asked you, how would you know if this parabola opened up or down? Go back to the original problem. Our a value is not really written there. It's understood to be 1. 1 is greater than 0. So this opens up. So you can see how vertex form puts at our fingertips the 3 main components, vertex, orientation, and the roots. And if they asked us for the axis of symmetry, I'll write it down here. It goes, what happens is I'll look up here. When we had this parabola, this was our y, this was our x. Wherever our vertex is, our axis of symmetry, my picture is pretty lopsided. But I'll draw a clean one down here. It doesn't match this equation here, but we would draw a parabola, say, the vertex would be down here, and our line of symmetry would be along that x value of the vertex. So for here, our axis of symmetry is going to be at x equals 2, because that is literally all you have to do is grab the x value of the vertex, and that tells you the axis of symmetry. Don't overthink that. It's a lot to take in. What you could do if you want another chance to practice this, since I'm not really going to have time to do another problem, we have a lot to get to in this video, I would grab your textbook, and there's a couple of examples underneath the examples that they do in the book. So that's what I would try. All right, next one is over here. We're going to find the minimum and maximum values. I really feel like Algebra 1 and Algebra 2 cover this, and the steps are right there. Set y equal to, so when you're from standard form, you're going to set y equals to 0. Make sure all of the other terms are on the same side as the x squared. And then to find the x value, you do the opposite of b over 2a. And then once you get that, you just plug it in. So we're going to do a couple of those. The first one is we'll take this problem. It says in a baseball game, a batter hits a baseball with an initial speed of 80 feet per second. If the initial height of the ball is 3.5 feet above the ground, I guess that makes sense, about shoulder height or whatever between the hips and the shoulders. The function below models the ball's height above the ground in feet as a function of time in seconds. What is the maximum height of the ball before it falls to the ground? I don't know if this is like a pop fly or a line drive, but maybe we'll get some information from this. So I am going to find some blank paper and put this equation at the top because I don't want to use the tools in the Pear Deck. Okay, whoops, it would help if I wrote down the equation first. Sorry about that. So the equation that they gave us is h of t equals 80t. And you can see that 80, that corresponds to the initial speed, minus 16t squared. If I remember my physics right, that pertains to the gravity coefficient. They're asking us to find the maximum height. So when I teach this in Algebra 1 and Algebra 2, I ask my students to literally write down what the a value, the b value, and the c value are. This is in standard form. A value is always the coefficient in front of the t squared or the x squared, so that's a negative 16. Our b value is the coefficient in the linear term, so that's positive 80. And the c is the constant in our equation. So then to find the x value of the vertex, we take the opposite of b over 2a. So once you have these, you know what they are, you just plug them in. Notice I said the opposite of b. I don't teach it as saying the negative b, because sometimes b is already negative, and that confuses people. So b is 80, the opposite of that is negative 80, divided by 2 times negative 16. So we're going to have a negative on the top and a negative on the bottom. So what we're going to do is make sure that they cancel out. So we have 80 over 32. And we'll get a value of 2.5 when you divide that out. So we're halfway through with the vertex, right? If they're asking us for the coordinates of the vertex, we know the x is 2.5. And what we're going to do now is find the y by grabbing this x value, and we're going to put it in here. I've been calling it x, but I guess in this case it's actually a t, right? It's the number of seconds. So we know that the ball hits the maximum point at 2.5 seconds. This ball is going really fast. It reaches the top of its arc as it flies over the baseball field 2.5 seconds after it leaves the bat. So all I'm going to do now is I'm just going to grab my calculator. I'm going to do 80 times 2.5 minus 16 times 2.5 squared plus 3.5. And I'm just going to see what that gives me. Minus 16 times 2.5 squared plus 3.5. Double checking that I typed it in right. That looks great. And when I plug this into the calculator, I got 103.5 feet. I know my y value is in feet because they told us that in the problem. So 2.5 seconds after the batter hits the ball reaches a maximum height of 103.5 feet, and it starts to fall back towards Earth, and it'll get lower and lower. Okay, so that's one way that we could use it in a real life application. That's why the vertex can be handy. Like I was also thinking for people that shoot fireworks off, that sort of thing, like all of that would be super critical. Like what's the height? How far out is it? Where do we make sure the crowds gather so that we're not having anybody get hit? So that could be another example of like, a legitimate application. That's the word I'm looking for. I'll do some that don't actually have like word problems behind it, just so that you're feeling comfortable with the mechanics of this. So if we're finding the maximum or minimum, we're given this equation. Again, what is the A? What is the B? What is the C? The A is the number in front of the x squared, which is not written here, so it's understood that there's a 1 there. The B value is a -2. And again, don't forget the sign in front of it is married to it. And C is the constant. That's the number that doesn't have an x next to it. And then the x value of the vertex, opposite of B over 2A. And again, if you're feeling confident, like pause it right here and go get the vertex and come back and hit play. Opposite of B is going to be a +2, right? Our B value is a -2. We take the opposite of it. In the denominator, 2 times A, that's 2 times 1. And so the x value of our vertex is at 1. And then we put the 1 in both places here where there's an x. So for the y value, we're going to have 1 squared minus 2 times 1 plus 1. So that's 1 minus 2 plus 1, which will give us 0. So our vertex for this parabola happens at 1, 0. If I asked you which direction or what was the orientation of this parabola, look at the x squared term. Again, our a value is 1, so that's positive. So our parabola would have an orientation of opening up. One more example of this. Again, hit pause if you'd like to and go through the motions and then come back and hit play and see if you got it right. Again, I start with the A, the B, and the C. A is 2, B is -8, C is -5. To find the x value, it's the opposite of B over 2A. And all of these steps that I do, I call it good math housekeeping, especially if you're new to this. Honestly, when you're doing it, write these down. They help you. It keeps track of what you're doing, and it's a lot harder to make mistakes if you're writing out all of these steps. Eventually, you get good at it. You can probably go a little faster and skip some of the steps. Opposite of B, the opposite of -8 is +8. 2 times our A value is 2. So 8 divided by 4 will give us 2. So our vertex has an x value of 2. That's also the axis of symmetry, correct? And then to get the y value, I'm going to put in, for the x values there, I'm going to put in a 2. And again, you can grab a calculator if you're happier doing that. That's fine. So that's 8 minus 16 minus 5. -8 minus 5 gives us a -13. So this parabola has a vertex at 2, -13. The parabola opens up. Our a value is positive. We don't have the roots from this. Maybe we could factor it or apply the quadratic formula. Any of that would work, hopefully, to get the roots. And then we'd be able to graph it. Okay, I think that's what I have for that. Let's see if there was anything else. I feel like there was one more set. All right. I don't have anything else on the pair deck that I'm sharing. So, here it is. The other part that I wanted to go over was how do you write a quadratic equation given the vertex and a point on the parabola? So, in other words, if all they tell us is here's the vertex and this point lies on the parabola, we need to come up with an equation. So what we're going to do is we're going to write out, so let's see, y equals, I'm just trying to not go too fast, h minus k, x minus h, actually I'll just write it out with all the letters first, and then it's plus k. So this was our vertex form, and what I'm going to do is this should be in your notes, and now we're just going to plug in things. So for the vertex, when they give us the vertex, we can immediately label these things h and k. Okay, so now what it looks like is y equals a x minus, there's our h, plus k is -2. I know it feels a little awkward because we have a minus and negative, so we might as well fix that. And usually we don't write it as plus and -2. So when I go to rewrite it, I am going to try to clean it up a little bit more. I have an x value and I have a y value, and they are right here. Okay, so when I clean this up now, I'm going to, wherever I see an x, I'm going to put in -1. If I see a y, I'm going to put in 0. So here's the y. That's going to be 0 equals, I'm going to copy the a because that's what we're looking for. X is -1 plus 2 squared. And then I'm just going to write that as -2. So we're kind of looking for the a value so that we can correctly write out our vertex form, and then we'll have the equation. So we're just going to solve for a. If I add 2 on both sides, I have this. And let's just apply order of operations. -1 plus 2 is 1. 1 squared is 1. And all of a sudden our equation has gotten very simple very quickly. We're just saying that 1a is 2. So a equals 2. What we're going to do is I'm just going to rewrite this over here. A, just where there's a little bit more space. So to write the equation, I'm going to keep the y as a y. I'm going to keep the x as an x. I need a number here, here, and here. They gave us h and k. We just found a. So y equals, our a value is 2. We're keeping the x. And then our h value is -2. So minus a negative becomes plus. And then our k value is a -2. And so that is the equation for that parabola. Okay, I'm going to do another one. If you're feeling it, then hit pause. This is something that isn't always covered in Algebra 2, so it makes sense to me that it might not kind of flow yet. For this example, I'm going to start just by writing that equation, x minus h squared plus k. So the vertex is at 3, -25, label that h and k. And -3, 11 lies on the parabola. That's going to be the x and y values that we're going to use. And so I'm just going to copy this. If I have an x, I'm putting an x. If I have a y, I'm putting in y. When I hit the h, I'm putting in 3. When I get the k, I'm putting in -25. So y is 11 equals, we don't have the a, x is -3 minus h, which is 3 squared. And then it says plus the k value, and k is -25. So I'm just changing it to -25. And then let's just add 25. That'll give us 36 equals a. And then when we clean this up, -3 minus 3 is -6. -6 squared is 36. And you can see that to solve this, again, this is 36 equals 36a. We would want to divide, but we get that a equals 1. Okay, so our final equation is we're going to copy this. We're going to put in our vertex here and here, and we now have an a value that we can put in. So our equation is y equals, and most of the time, our a value is 1. Most of the time we don't write it, but just for emphasis on this problem, I will write it so that you're like, what happened to it? Now you'll be able to see it. And that would be the equation. If you wanted to put it in standard form, you would square out the binomial and then just combine any like terms, and you'd be done. I think I have one more of these. Just looking really quick, making sure I covered them all. That one's a convert. That one is not a convert. There we go. So in this equation, the vertex is at 0, 4. Label it h and k. And -3, -5 lies on the parabola. Label those x and y. And remember that what we are trying to come up with is a lot of information to put in here. Okay, so I'm going to recopy it. We have a y value that they gave us. We do not have an a. That's what we're looking for. The x is -3 minus our h of 0. And then finally plus k. We'll start by subtracting 4. And then cleaning this up. -3 minus 0 is -3. -3 squared is 9. So we have that -9 equals 9a. Divide both sides by the 9. And we'll get that a equals -1. So our equation is going to be y equals -1 x minus, and h is 0. So actually, since we have a 0, let's just keep it as -1x squared. -1x squared plus 4. Okay. All right. Those are the main ones that I wanted, the main kind of problems that I wanted to cover in this lesson. Like I said, I do encourage you to go back and look through the chapter and see if there's any other things that you're not sure about, and make sure you take notes on those as well. All right. Thanks for tuning in.